So let's move on now to the presentation by George Strong, and Doug will be introducing Dr. Strong.
Okay, I'm delighted to introduce George Strong. He's long been a colleague of mine. We, in fact, share institutions. My degree was from Iowa State University as an undergraduate, and George, in his career, was the director of computing at Iowa State. So we've known each other quite a long time. George has an extraordinary career. He's now the Director Emeritus of the Board on Research, Data, and Information at the National Academies of Science, Engineering, and Medicine. And he's focused on open science and fair data there. He does continue this work as a National Academy of Science scholar. Prior to joining the academies, he was the director of the National Coordination Office, NCO, of the Networking and Information Technology Research and Development Program. We call it NITRD, and co-chair of the NITRD Interagency Committee. The NITRD is the key coordinating organization for information technology at the federal government level. And Dr. Strong held those positions while on leave from the NSF, the National Science Foundation, where he was seconded to the Office of Science and Technology Policy in the White House. He was the National Science Foundation's Chief Information Officer before this. I also need to share with you that George had quite an extraordinary challenge in bringing this to you, because he came down with a kidney stone just as he was in the process of creating this presentation. So we're extremely grateful for George's ability to persevere and record this presentation. And thankfully, his procedure went well, and he will be able to join us for the Q&A at the end. So I give you now George Strong.
Good day, ladies and gentlemen. As you can see on the slide, my name is George Strong. I'm very happy to be here with you today. I'm sorry that it's in a pre-recorded format rather than live. Turns out I'm dealing with a small medical issue. I'm told it's about 4 millimeters. And tomorrow it should be all taken care of, and that means Wednesday I should be feeling up to joining you for a live Q&A. But just in case that doesn't work out, at least you have my remarks for you. First of all, I'd like to thank Doug Van Houweling for the invitation to join you. Computable knowledge, or knowledge and computing, have been topics on my mind for some time. Back when I was CIO at NSF in the early part of this century, they then asked me to be Chief Knowledge Officer and Chief Privacy Officer. Fortunately, I only had to appoint the Chief Security Officer, which was something I didn't care to be. And anyway, I've stuck my nose at that point in time into what knowledge management meant and what it was becoming to mean as we move more into the computing era. And in the last decade or two, I've been working on open science and fair data and other matters, all of which I think seem to come together very nicely. And I've been reading information philosophers on the subject of information and knowledge. So this is an attempt that I'm very happy to have had to put together my current thoughts on the subject. I guess there will be some either unclear or controversial areas, which I hope will be discussed in the Q&A afterwards. This is an extremely important topic, and I'm very happy to be a small part of it. What I will do is talk about a few ancillary subjects under the title of The New Renaissance, Open Science and Fair Digital Objects, before getting into the heart of the subject, which I call computable knowledge of type 1 and computable knowledge of type 2. These are my designations, and so I'll do my best to explain what I mean. I think computable knowledge of type 1 is consistent with your ideas about computable knowledge, but let's see. To be more specific, I think computable knowledge of type 1 is compute-enabled human know-what. And yet I think there is a second type of computable knowledge emerging, which I call type 2, which is computer know-how. So let me proceed with my background information and then proceed to those subjects. About 20 years ago, a computational scientist named Robinson wrote a book with the title The New Renaissance, and he structured all of human history around the four major occurrences of spoken language, written language, printed language, and computed language. By the way, I've given references on the last page of these slides to the various things I'm referring to, so should you care to look that up, which I think is still a good read, you're welcome to find it there. Elizabeth Eisenstein, in a large book some years ago called The Printing Press as an Agent of Change, outlined the hugely important subjects that printed language had given to Western Europe that it hadn't had beforehand. Such things as a sustainable Renaissance, the Protestant Reformation, the Scientific Revolution, and other things as well. The point is, printed information has had a defining impact on us in the last 500 years. And his point, which I agree with, is computed language, which we are just beginning the journey, will, from a vantage point of several hundred years forward, probably have created as many important and unforeseeable changes in the world as printed language did. So it's an exciting venture to be involved in computed language, computed knowledge, all of these subjects with a number of words which are sort of acquiring new meaning. One of the subjects that my work has been involved with in the last decade, at least, is open science. We've always, in one sense, open science is somewhat redundant. Science has been an open endeavor since the 17th century, when the Royal Society said we scientists should publish our articles. Actually, it was natural philosophers, since there weren't any scientists till the 19th century. But times have changed. Now in the 21st century, open science can mean something entirely more expansive. Can mean sharing all scientific outputs, articles, data, software, workflows, etc. And once we will do so, it, in my mind, could amount to a new scientific revolution, as important as the 17th century science revolution in terms of the additional capability that this new model will give scientists to stand on the shoulders of people who have gone before. And the reason I want to say sharing rather than publishing is because it involves planning the entire sharing process before the experiment begins, rather than writing up the results at the end of it. Of course, these outputs should be machine readable and, where possible, machine actionable, because, as I like to say, many of your readers, your new readers, will be computers, not just other people. Several years ago at the academies, we published a consensus report called Open Science by Design, which I commend to your reading. It's also found in the bibliographic material at the end. One particular technique that I've been involved with at the policy level, not with the actual implementation level, is a subject called FAIR digital objects. FAIR, as I suspect you know, is an acronym for findable, accessible, interoperable, and reusable. I was at a workshop in Leiden, 8 or 9 years ago, where that acronym was created. And when the results were published up, it's an article that's been not only read innumerable times, it's also been referenced innumerable times. So I would be surprised if you haven't heard it since then. And tell me, has there ever been a better acronym? Who can be against something that's fair? And if you decode the algorithm, even there you find acronym, you find important things. The difficult thing, of course, is interoperable. Today, when scientists try to munge together data from different experiments for a joint experiment, a joint review, the estimate is that 80% of the time is taken up with getting the data so that it will play together, understanding the data well enough, which is a highly human endeavor, to put the data together properly. I suspect it may be a fool's errand at this point, thinking that we can get humans entirely out of that loop. But if we could cut it from 80% to 20%, or make the human involvement extremely more efficient, that would be really a great benefit for the interoperable dimension of FAIR data. And I think using human intelligence efficiently is basically a subject that we're talking about today when we talk about computable knowledge. Anyway, the back end of FAIR digital objects are digital objects, which illustrates one, I think, fairly well thought out way of making data a first-class citizen in the computing environment of the future. An assemblage of the data, the appropriate metadata, and reference, a permanent identifier, permanent global identifier that points at the data and the assemblage of metadata. Only 2 protocols in general need to be defined to associate the implementation independent permanent ID with an implementation dependent address. That would be an internet address today, for example. But this is a goal of having something that could exist for 100 years, which is a wonderful goal in an era, in a society that thinks nothing but short term. Anyway, this is not a lecture on FAIR digital objects, so I just want to mention I think it's important. One reason it's important is because AI is so important these days, and making more data AI ready has got to be an important ancillary task as we move into, quote, the AI era, at least if things proceed as they will. And this may be a little bit like in days gone by when supercomputing was an issue in the academic community. And as an ancillary effect, the expansion of supercomputing was recommended that a network be connected to research universities so that investigators wouldn't have to go to the supercomputing centers every time they wanted to initiate a job. Well, from that humble beginning, the mighty internet was born. And perhaps from the humble beginning of making more data AI ready, maybe the open science world can in fact be born out of that special usage. Bear in mind too that we can distinguish between capital D data and regular data, because not only data, but the articles and the software and the workflow and everything all has an implementation as digits, as data. So digital object, as discussed above, is suitable for all of those artifacts, not just for data with a small d. Chetan Baru at NSF has a good way of phrasing it in my mind. He says one of our goals is advancing data from output to infrastructure. Well, I'd say that that's been accomplished for hundreds of years with articles, right? By the time you write up an article and it's subject to peer review and exists in journals, it becomes part of the infrastructure which scientists use to go to the next level. Well, our goal is to be able now to do that for data, for software, for workflows, et cetera, as we proceed with a new definition of open science. Rather whimsically, I like to say there are three phases or three generations of computing. The first one from 1950 to 1995 with many computers and many data sets. But then with the commercialization of the internet in 1995, we have one computer and many data sets. This sort of plays off Sun Computer's old marketing slogan that the network is the computer, although our data sets are still not interoperable, so we have many data sets. I'm putting a hope on 2030 as the termination of item 2 that we will have figured out in this coming decade how to greatly improve the ability of making data interoperable. The more efficient that can become, the more important it will be. So that after 2030 or sometime, our environment will be one computer and one data set. Last comment on these matters, which of course applies to computable knowledge as well as other modern approaches, is data infrastructure. Europe talks about the open science cloud. NIH under Phil Bourne talked about data commons. Other names might be used or created in the future. When will these occur? Well, Europe is already putting money into the European Open Science Cloud. U.S. is still in consideration of whether there will be a unified national effort in such a fashion. Part of all this is, of course, a question of who pays and how one pays and whatever. And just to point out that we talk about commons or clouds, but where to put the data is less important than how to put it. Putting the data with appropriate metadata and other capabilities to promote interoperability is the real challenge of the decade. So with those preliminaries out of the way, let me return to the central subject of the discussion of knowledge. Of course, if you look on the web or elsewhere, you can find many definitions of knowledge and many definitions of different types of knowledge. We can go all the way back to the philosophers and talk about the subject of epistemology, which is the big name for theory of knowledge. But the two dimensions I want to talk about are know what knowledge and know how knowledge. The first one is knowing facts and information, that is human know what knowledge. And again, the emphasis is on the humans, what do they know? And skills, where I will claim that now humans and machines can have a certain degree of know-how knowledge, and this complicates our world going forward, probably for the better, but with some concerns as well. There are many ways to acquire knowledge. We'll talk about some in the future. Until recent times in our tradition, it was understood that only humans had the ability to have knowledge. Because of what I've said above, I'm going to show, I think, that there's at least one case where computers now can be said to be knowledgeable. I'm sure you've heard the phrase knowledge graphs, which seems to be the data technique of choice at the moment that's being pursued to represent data. it harkens back to a well-understood entities and relationship form of graphs, where the nodes of the graph are entities and the arcs between the nodes are relations. The academia has picked this up, private sector has picked this up, and in one sense, it's just a reincarnation of the type of structures that the semantic web and its son linked open data have been talking about for the last 2 decades. But it's in a state of considerable development right now. So the notion of a knowledge graph ought to be considered more than a precise notation or a system, but it's an evolving project and a vision. All right, well, all of that with preliminary, let's get down to business of talking about computable knowledge, at least as I understand the phrase. There is a list of computable knowledge applications that you will find if you Google knowledge, computable knowledge, and one of the references that comes up is this page from the Wolfram data repository. And there's approximately one development per year since 1960 that is categorized by him as computable knowledge. Therefore, you can see it's a broad thing, and in general, I believe they're all referenced to what I've talked about as computable knowledge of type 1, where a computing environment makes it easier and much more efficient for humans to acquire new knowledge. Let's say a little bit about semantics and the standard hierarchy of data, information, and knowledge. Data is what you find in computers. It's stored in computers. It's communicated between computers and humans. It's transformed by computers for presentation to humans. Information, at least from a philosophical standpoint, is meaningful data. Meaningful words, meaningful sentences, meaningful articles. And as the information philosopher Luciano Floridi points out in his books, humans have the only semantic engines in the world. That is, we are the only ones that can understand meaningful information. Hence, by that definition, there is no information in computers. There's just data. Knowledge, of course, lives in people and in their languages based on meaningful information. Hence, you could say that in computers themselves, at least typically, there is no know-what knowledge in computers, as well as no information in computers. So, getting back then, what is computable knowledge? And let's look at a couple examples. Take a simple example, which should not be underestimated in terms of its importance, namely the World Wide Web and searching the World Wide Web. I'm told the web now consists of about 1 trillion documents hyperlinked together. That's all explicit knowledge. And the semantics are all provided by the humans who look at those pages, because presumably you can look at them in a natural language that you're familiar with. Web search, this wonderful application, is enabled by creating a humongous data structure that links documents and their contained words. Semantic engine, that is a human, specifies meaningful words, and a search engine computes a list of the documents containing those words. That's a rather brief description of what you know is a revolutionary application, especially if you can put the most pertinent pages, or the pages that are expected to be most pertinent, up at the top of the list, since the list can be millions of pages long. In any event, having specified meaningful keywords, the human scans the document list for meaningful documents. Thus, the human has possibly gained knowledge from this computed data, hence computable knowledge of the first type. That is, computer-enabled human know what. A very nice step in the right direction. But let's talk about generation 2 of this type of service, which I think is even more exciting. Many of you in the audience may be familiar with Semantic Medline, which was an experimental system developed at NLM over the last 2 decades by Tom Rindfleisch and his colleagues. Medline, as again, I'm sure you know, it consists of tens of millions of titles and abstracts of biomedical research articles. And humans could, and in fact do, submit keywords to look for articles in Medline, just like you can do on the web. But Semantic Medline is more ambitious. Rindfleisch and his colleagues have, for the last 2 decades, developed a natural language processing program which looks at the abstracts and finds the key sentences which describe the results reported in the article. Rindfleisch said that he suspects on the average there are 4 key sentences per abstract. His program, he also notes, can find 3 out of the suspected 4. So not perfect, but a pretty good step. Now, if you take those key sentences and you simplify them down to a triple called a subject word, a relation word, and an object word, if you further restrict those words to a controlled vocabulary, such as Unified Medical Language System in NLS, then the set of all key sentences can be called a knowledge base. But not a knowledge base because the computer can understand the knowledge, but because it was going to help humans obtain knowledge much more efficiently. For example, 2 medical facts of some standing were that aging men have this decreasing testosterone and aging men have increased sleep problems. I do present myself as facts in evidence of these 2 statements. And for some time, the medical community did ask, are these 2 facts related? Well, because of the wonderful AI, because of the wonderful computational capability surrounding Semantic Medline and similar semantic web applications, there's a language called Sparkle, which is a search language, and you are able to form a query that you see there in front of you, where the only 2 words that you know are sleep problems and testosterone. So you say, well, is there somewhere a key sentence that says testosterone is in relation 1 to some common word? And is there another word, another key word somewhere that is in relationship to, or key sentence, word relationship to sleep problems? A lot of variables in there, but you see it's connecting information between documents, not just looking at individual documents. And voila, the search results that come back after a search query like that is testosterone inhibits cortisone, which was a statement, a key statement in Article 1, and in a second article, cortisone causes sleep problems, part of the results of Article 2. It's fairly clear that no individual scientist read both those articles. Otherwise, they would have done something like this beforehand, before Semantic Medline caught it. In other words, a new scientific hypothesis was computed from the scientific literature, and therefore that hypothesis and the human knowledge gained from subsequent experiments can also be called computed knowledge of type 1, because the human knowledge is gained with great efficiency via the computing structures that have been created. Now, looking ahead, I'm told Chuck Freeman is here, and at this point I'll stop and tip my hat to Chuck. He and I had some dealings when we were both in D.C. about a decade ago, and it's good to reform this electronic connection with him. The Chuck's circle, which I also show on a slide just to show you that I have seen it written down, with respect to health problems of interest, where the rising part of the circle is data to knowledge. The keystone of the circle is the knowledge that is gained and recorded, and then the knowledge is used in practice to give better practice, and probably more data is accumulated that is then to be turned into knowledge subsequently. But let's what I just said is the first bullet, data to knowledge, which is doing science in general, not just medical science. Knowledge to use is the practice, again, of whatever, and the practice creates more data with the opportunity of doing more science. So if we can say then, well, let's do a data to a knowledge base, that's doing open science. And knowledge base to use, that's efficient practice, such as the example from Semantic Medline shows. And again, more data is produced and we're back to practice. I've already mentioned that Semantic Medline uses natural language processing. There's another approach to this subject that's been popularized more in Europe than here, called nanopublications, where nanopublications are in fact the key sentences that I described in Semantic Medline, but rather than using natural language processing to dig out the key sentences from the abstracts, the proponents of nanopublications suggest that it won't be that hard for the researchers to gain the expertise to write and publish their own key sentences along with the human readable abstracts. Well, that's as may be, and some people think that the investigators may have enough time to do that. Some people think they may not. In any event, what the future needs to bring us is the ability to automate this knowledge acquisition. And if that were to happen, and I will suggest I will be talking in a couple slides about deep learning, the rock star of the AI portfolio right now. And I'm told that there is some work going on already to see whether deep learning could create these knowledge bases. If they could, then of course that would mean they would deduce a controlled vocabulary. They would deduce all of the key sentences from all of the published literature. I'm dreaming, of course, but I could see this as a project for the coming decade as well, that if all science disciplines did this, we could end up with a knowledge base of the literature of each scientific discipline, which would be at least a wonderful place to begin to develop an all science knowledge base, enabling better interdisciplinary open science. Much work would remain to be done there as we are able to rectify and make interoperable the controlled vocabularies and the key sentences from each of the disciplines. So don't anybody think of retiring. There's plenty of work to be done looking forward. One last look at Chuck's virtuous cycle. And on we go to computer know-how, type 2 knowledge, and by my suggestion. Well, and to give a simple example before I get into the more interesting example, semantics of programming languages is a subject that I used to dabble in years ago before I turned into a policy wonk. And one of the forms of semantics of programming languages is called operational semantics. That is, you describe the meaning of a valid program together with some valid data for that program as the computation resulting from executing it. Well, that's not what the computer knows, but what the computer does. So if we're talking about what computers can do as opposed to what they can know, perhaps it's fair to say that computers can implement semantic engines for knowledge of type 2. And I do say computer knowledge as opposed to computed knowledge, because I want it to be emphasized that it is the application itself that demonstrates the know-how, as opposed to making it easier for humans to have the know-how. The words that we haven't formally discussed yet in this panoply of technical terms that are sometimes used semi-technically: knowledge or intelligence, the ability to acquire and apply knowledge and skills. So obviously a direct connection between intelligence and knowledge in that regard. Artificial intelligence, subject that we computerists have been working on ever since the days of Alan Turing. And one definition that you'll find online is that a system's ability to correctly interpret external data, to learn from such data, and to use those learnings to achieve specific goals and tasks, that is, know-hows, through flexible adaptation, which means flexible programming. Deep learning is, as I say, the most successful dimension of AI programming at the moment, most in the spotlight. Deep learning is the new term associated with artificial neural networks. Artificial neural networks were defined by McCullough and Petz in a 1943 article, giving a model of how neurons worked, but saying, why couldn't we use that model for computational purposes and see what would happen? In the history of computing, neural nets were studied then in the 40s, the 50s, and the 60s with some interest. But by the end of the 60s, two knowledgeable people in the field published a paper saying there is only limited power in artificial neural networks, and we're wasting our time studying them. These were sufficiently influential leaders of the field that the research money died up for artificial neural networks, and it entered its phase of a AI winter, which has happened in various AI disciplines at various times. But in the 90s, several intrepid investigators began investigating the subject again. First of all, with much more computing power than had been available before. And secondly, they found that several of the assumptions that the learned people had said about limitation of power of artificial neural networks were just flat wrong. The learned people had said that an artificial neural network with hidden layers in the middle wouldn't be any more powerful than an artificial network with just one layer, going from input through one layer to output. Well, that was proven to be greatly mistaken. And with more layers, more hidden layers in the middle, artificial neural networks come to great power. That's why it's called deep learning. I think the deep is relating to the fact that you have multiple levels in the artificial neural networks. So what has been done in this subject matter? Reading the next bullet from right to left, I guess this subject got its first glimpse of public popularity in cat pictures. Could find all the pictures of train it with some data that says this picture has a cat in it, and it can go off and find a million more pictures of cats on the internet. It was then applied to a slightly more useful technique of changing speech to text. We now have all sorts of Siris and Alexas and whatever which will in fact take the verbal speech that you talk to it and create text out of it, which is much easier to process by computer applications going forward. And even more spectacular is the language translation in general. And the way deep learning works, I'm sure you know, is you give, just as the definition of artificial intelligence is there, you learn from external data, that is a bunch of already existing translations, and then use those translations to create more translations just based on how it was done before. Now, what goes on inside with the parameters being set at these various internal levels is a mysterious activity. But the last article I read about language translation says it's machine translation is 95% successful. And if you do that for most cases, that's good enough. For places where you really need a perfect translation, a native speaker, a trained translator can provide the final touches much more efficiently than starting from scratch. So these are all very interesting applications. But last fall, the best application of deep learning was announced in Nature. Protein folding, subject I'm sure that's near and dear to your hearts. Deep protein folding, deep learn, quotation from the Nature article, Google's deep learning program for determining the 3D shape of proteins stands to transform biology, scientists say. I remember the first time I heard about protein folding some decades ago. It was estimated at that point that one protein could be folded by one supercomputer after 1 year of processing. So the amount of computation required to do such a thing was daunting, especially since I believe there are about 100,000 proteins. That looked like a number of supercomputers and a number of years into the future before we could do such a thing. Now with this deep learning application, in hours or in some cases minutes, a protein can be folded with the same degree of accuracy that the very complex and difficult experimental process to check the folding can actually be uncovered. So here we have an activity of this new type of programming, this deep learning program that has solved what could be a transformative question in terms of biological study. But is this know-how without know-what? I recommend the book Homo Deus by the historian Yuval Harari, which is his second book after writing Sapiens, which perhaps you have read also. And he puts it in more or less philosophical terms. We all agree that the computer does not know what we mean, as I said previously, but with applications like deep learning, the computer does do what I want. And that it does so in an increasing array of tasks that, at least up to now, we have always thought required intelligence. Whether it's playing chess or playing Go or doing all of the applications we've seen on the previous page, this new technology, this new computing technology will do things for us that are superhuman in the sense that even the Go masters and the chess masters can't live up to that standard of behavior. But Harari asks the question, well, will we be happy with an increasing amount of intelligence, that is the know-how, without consciousness, which is the word he uses, but that's rather fuzzy from a scientific standpoint, so let me substitute know what. That is, as we increasingly get deep learning results of know-how, but with no consciousness there, with no what, no ability to explain what was done, how happy will society be with that? I guess, we've already had some pushback about that already with complaints that if we accept deep learning results without being able to explain how they were achieved, who knows what biases and other nefarious activities might sneak into the final result. Well, in effect, I'm done. This is my last slide. The subjects of data and knowledge have never been too far away from each other, but with the computing environments of the last 50 years, especially the advanced forms like semantic midline, offer computing environments for efficient acquisition of human knowledge, that is, human-enabled know-what. But also computer applications by deep learning produce new knowledge of the form of computer know-what without a human-readable, know-how, without a computer-readable know-what to back up what has been done. Anyway, going forward, since the last half of the 20th century, obviously the destinies of data and knowledge have become increasingly bound together by computing, and certainly we can expect this process to continue probably for the rest of this century. Very interesting time to be involved in these activities. With that, I thank you for your attention and have a good day.
Thank you, George, and hello, George. It's great to see you. Glad to hear you're on the mend, and thank you for being here with us live. It's wonderful to see you again after all these years from the days we worked together with NIDR-D. So we have some questions that we hope you will respond to, and this will give you a chance to elaborate on some of the things you said. The first question goes to this issue of data, information, knowledge, wisdom, the DIKW pyramid. Blackford Middleton argued that, in his humble opinion, wisdom is knowledge internalized and acted upon. And a similar question was asked, how does the notion of wisdom fit into your schema? Could you talk a little bit about wisdom?
Well, I could, but since I don't have a lot of wisdom myself, take my remarks with a grain of salt. Wisdom is obviously the keystone of that four-element hierarchy, and wisdom is well, I've seen multiple definitions of wisdom, just as multiple definitions of all those other layers. Wisdom is knowing how to use knowledge appropriately. So if you've got a bunch of knowledge and now you've got to take some actions one way or another, it's never a straightforward situation, but the wiser person will have more of a tendency to do the right thing based on the knowledge that he or she has.
Okay, thank you. Another question. What regulations or data/knowledge representation standards will be needed to support applying results from open science into different contexts of practice? Do we need to rethink the standards development and coordination to complement and enable open science?
The devil hides in standards as well as in details. And thinking back to the internet experience, we see some comparisons. We had in the 60s and early 70s a de facto development headed by DARPA that ended up with defining the TCP/IP protocols. And by that time they were defined, the international organizations figured that such protocols were going to be important, so they embarked on creating the OSI, Open Systems Interconnect Standards. But there was so much political argument and haranguing that those developments never completed before the internet was placed into wide use, and the de facto internet replaced the de jure OSI as the future that we are now living in the present. Regarding data, the biggest difference, I think, and the biggest disappointment to me is that we have no TCP/IP of data. If we had a TCP/IP of data, we could all pull together in that direction and begin the various applications and other types of common developments that could occur on it. In fact, we have a number of competing approaches, which is all right for a while, but until we come to a single standard, hopefully like TCP/IP, that is with the narrow part of the hourglass being where the required standards are, with the freedom to implement things in many ways in the lower half of the hourglass and freedom to develop many applications in the top half, with as limited as possible standards required in the TCP/IP equivalent part of the required standards. We're still, in effect, in the 1970s vis-a-vis the internet, in terms of looking for the standards that will indeed promote the open science and all of these wonderful blessings that I'd like to see will happen.
Thank you. A couple of questions relate to your prediction that we will move to one computer, one data set. One of them is, how do you see issues of incomplete or limited data or biased data and uncertainty of knowledge fitting into that one computer, one data set vision that you described?
Well, I'd be the first to admit that that prediction is as much a set of wishes as it is a set of hard and fast predictions. And I don't think it'll ever be done perfectly. We know that data is a fuzzy situation. There's incomplete data, there's incorrect data, so on and so forth. But I do think the idea of moving from 80% of the time spent munging the data together to at least 20% of reduced to at least 20% of the time of munging data will make these activities much more practical, and therefore they'll be used. And if we can really do that from 80 to 20%, then wise kids will come along and say, oh yeah, but why don't you do this, that, or the other? And all of a sudden we'll make progress in a way that we can't vision now. But the perfect is the enemy of the good, and we're pursuing the good right now, and the perfect may be out of reach.
Thank you. We have a question from Brian Alper that I'm going to defer and ask Brian to rephrase his question so it's a little bit clearer. So, Brian, could you do that and put it back in the chat so it might be a little easier, at least for me, to understand. Thank you. I'll ask a second question now about the one computer, one data set vision. Those of us who work in health domains, and I recall our joint excursion into that domain a decade ago, are very sensitive to issues of privacy of data. And I'm just musing about how this notion of one computer, one data set might sit with privacy advocates in health and maybe other domains where privacy is of such great importance.
Yes, health data, of course, as you just pointed out, has many privacy considerations. Proprietary data from the private sector has similar privacy concerns. Somebody's trying to make a product that they don't want to be scooped by someone else, and they have proprietary information. So one of the phrases that we use sometimes is that all data should be fair, and as much data as possible should be open. That is, understanding that there will be exceptions to open data in sensitive areas such as healthcare and commercial proprietary information. Now, if all data is in fact fair, then it seems if someone were to hack into your system, it'd be easier to use it in a nefarious fashion. So I don't think the clever statement of all data is open and all data is fair and as much as possible is open is the end of the battle, but I think it's a good place to start.
Okay, thank you. We have a useful expansion of Brian Alper's question, so let me put it to you now. If there are competing standards for data expression, and you believe there should be one and only one standard, do you have a suggestion as to which of the competing standards should be used?
Well, fine question. And it's one of the $64 questions of data. One of the ways we've tried to finesse that issue is thinking about interoperability between standards as opposed to a single standard. To me, it seems more likely that there will have to be something agreed to eventually, some minimal standardization that all of the other so-called standards would adopt, again, like the TCP/IP to compute to transmit messages from one computer to another. But again, knowing that that multiple work is going on and that everybody prefers their own efforts, and that we don't have existence proofs of what the best way to proceed is, thinking about interoperability between existing efforts is the thought of the moment rather than a dictatorial. This is the solution, and it's I had one more thought on it, but it's thrown out the room at the minute, so I'll stop there.
Okay, and that gives us time for one more question. Hyunju asks, the transition from computer know what to computer know how wouldn't be a natural progression. What do we need to focus on to make this transition?
If you believe Floridi, and I tend to, his works have moved me in a different direction. The fact that we will ever have computer know what is an open question. Maybe a long time before computers can actually know what is going on. We may remain the semantic engines of the world for the foreseeable future, in which case we have this conundrum of how do we work to explain computer know-how, deep learning results, to a questioning humanity who wants to know how you obtain that result. That doesn't seem to be too much of an issue in protein folding, where experts have weighed in and measured protein folding by deep learning versus experimental methods and so forth. And therefore, how it obtains it may not be a societal concern. But other methods where biases of one sort may appear, I don't know. I think it's an unsolved problem. To my knowledge, it's an unsolved problem right now of how we put human know-what on top of computer know-how to broaden the range of applicability.
Thank you. Well, this brings our session to an end here. I can't thank you enough for this presentation. I was sitting and riveted by many of the things you said, and we are just so grateful for your contribution to the meeting and wish you a continued speedy recovery. Thanks so much, George. Great to see you.
Thank you, Chuck. Same here.
So we will now reveal the results of the poll. I know you have all been waiting to hear this, as have I. In response to question 1, we had about 70 respondents to the poll. 70% approved of the plan as drafted. 20% said the plan required further revision and will send comments, and I guess that means 10% thought the plan required further revision but will not send comments. So we'll look forward to the comments further coming in, and as we said, we're planning a webinar, a town hall, not long after this meeting, date soon to be announced, to consider these issues around membership organization for CBK further. Question 2, 83% said it was highly likely or likely that their organization would join MCBK as a membership organization. And with regard to question 3, 87% said it was highly likely or likely that they would personally join MCBK as an individual membership organization. So thanks to those of you who responded to the poll. This is very important information for us to have as we move forward.